All right, then we'll hit distortion, part beam alignment, focus spot, and we'll go on from there. So one thing I did want to point out though is modulation transfer function is on page 211, your textbook, and it is kind of complicated to read through. So small items positioned close together are hard to identify as separate. Right, so that's pretty obvious. That's basically your line pairs per millimeter. Right, so small objects close together that are hard to differentiate. Our tool that we've taken a look at, the smaller the lines are towards the bottom of the scale of the line pairs, the harder they are to visualize. So then you have high spatial resolution is required to image those. But essentially, without good contrast, they don't really matter. You can have an appearance of poor resolution just by virtue of having poor contrast. So where the computer manipulated image shines and where we really get a benefit is in that dynamic range. So where things tended to blend together because of poor contrast before with the superior dynamic range of the computer processed image for the computer algorithms and all that, where we can ferret out that contrast. We might not have quite as good actual resolution. It's probably going to be pretty close. It might not be quite as good, but because of the improvement in the contrast, and then we get the appearance of better spatial resolution. We can see those lines, even if the lines are a little bit bigger than what they otherwise would have been. We could see the lines as opposed to them all blended together because of low contrast. So for our purposes, what we're going to call modulation, what we're going to call modulation trade, or how we're going to define it. Stumble through that. How we're going to define it is kind of like spatial resolution married to contrast resolution, because without the contrast resolution, spatial resolution doesn't really matter at all. So magnification, you say we finished that up last week. Of course, size distortion occurs SID, OID, get a loss of sharpness, recorded detail. We've got the ways that you can calculate magnification factor. We did say that it's always greater than 1. We did take a look at these images, about L-spines in context of how we would better shoot them, AP versus PA. Remember SOD, how to calculate SOD, source to object distance, how to control magnification, always lowest OID, longest SID practical. You don't want to shoot everything 7.2 inches. Okay, so macro radiography, I think we did not really touch on, correct? And talk about macro radiography. So what we have in macro radiography is intentional magnification radiography. And it's kind of, I don't want to say it's gone the way of the dodo bird completely, because we still have to have magnification radiography, but how we get to it is a little bit different. Traditionally, what you had and where you see this is in special procedures in cardiac catheterization. They use C-arm, right? And the intention was with the C-arm, you've got on one end, you've got the image intensifier, and on the opposite end, you got the X-ray tube. And traditionally, the smaller of those two ends is going to be your X-ray tube, and the larger of the two is going to be your image intensifier. So with a C-arm, you can change your OID and your SOD. You can't really change SID, right? It's locked into place. So you can change where the patient is in that, and therefore change your magnification. And in special procedures, and especially cardiac catheter, let's say special procedures, what they would do is put the patient's skull in the middle of that, so for a couple of different reasons. One is that the X-ray tube is down here and the skull is in the middle of it, and we need to fix an aneurysm in the patient's skull. It's in a small artery, then we need that magnification, right? So we have intentional magnification with an intentional increase in OID. Can't change the SID in the C-arm. You wouldn't want to anyway. You need the increase in image size. All right. So it's an intentional increase in OID so that we can magnify the artery and make sure that we're in the right place. So it's an intentional increase in OID to give us an increase in magnification. So test questions, we'll ask you about macroradiography and how you overcome the inherent loss of sharpness as you increase that OID. How do you increase the sharpness of recorded detail when you increase OID? SID. Right, but you don't increase SID with macroradiography, right? And that's the answer you're going to have a tendency to jump on. But you don't want to do that because you do reintroduce the sharpness of recorded detail, but what do you reduce? It's magnification. You want the magnification. So the only way that you can overcome the loss of sharpness of recorded detail is with an even smaller focal spot. So if you remember all the way back to physics in the first semester, we talked about different types of X-ray tubes and different types of focal spots. We had fractional focal spots and microfocus tubes. And special procedures uses a fractional focal spot. So the focal spots you use are larger than what they use in special procedures. The reason they use those in special procedures is to reintroduce that sharpness of recorded detail because of the intentional increase in OID. You don't want to increase SID. You can't increase SID if you're using a C-arm setup. If you're using a U-arm setup, which is a totally different thing, then you might be able to, but with a C-arm setup, you cannot increase SID, right? You can't expand the C. You just can't. So they use fractional focal spot. Now, they still use those in special procedures, and they still use C-arms for the most part in fluoroscopy, but how they magnify now is just digitally, right? They still have to have that sharpness input, so they're still going to use those same X-ray tubes, but rather than having the head in the center for the sole purpose of magnification, it's really, if they're just using a single C-arm, it's really convenience more than anything else. And that is because, you're putting stuff into a patient's brain, right? So you want to do that as quickly and as efficiently as possible. So what they'll do is if they're just using a single C-arm setup, most of the time they're going to use two C-arms, but if they're using a single C-arm setup, then if the skull is right, and the anatomy of interest within the skull and inside the brain is in the center of that C, and they rotate that C, it remains in the center. Does that make sense? Okay, so it's convenience as much as anything else now. But it's still testable. Macroradiography is intentional magnification and involves an increase in OID, and it requires a fractional focal spot so that we don't lose the sharpness of reported detail. Don't jump on increase SID to overcome the loss of sharpness of recorded detail in macroradiography. You don't increase the SID because then you'd reduce magnification. You want the magnification. This is intentional magnification radiography. This is macroradiography. Okay. So distortion, we took a look at that in the presentation earlier. So with distortion, you've got two different types of distortion. We saw both of those. You have a central ray angulation, you're going to get some sort of distortion. And you have anatomy angulation, you get a different type of distortion. Sometimes the elongation, like in the bottle elongation, may be a little bit difficult to identify exactly, but with central ray angulation, you typically get elongation. With part anatomy angulation, then you get foreshortening, right? So this thing is, I think it's 50, it may be 48, it may be 48 inches long. So that's 40 inches right there. So it's 48 inches long. So we've got 48-inch shadow here, and we've got not 48-inch shadow there, right? So anytime you have dissimilarity, non-parallel relationship between the image receptor and the anatomy, you've got angulation, right? Which is going to give you foreshortening. only way that you can bring that back is to make the central ray match the angulation of the anatomy, right? So also, though, if you have, let's say, for elongation, if we have an angulation on our central ray, we're going to introduce elongation. But also, if we have a perpendicular central ray, and we have an angled image receptor, we also introduce elongation that way as well. So central ray, image receptor, we've got elongation where we have angulation of the anatomy, we have foreshortening. Both are unequal magnification. All right, so on your task questions, if it asks about unequal magnification, it's going to be foreshortening, it's going to be elongation, it's going to be a question about distortion. All right, so if I'm asking you a question about size distortion, that's your magnification. Okay, so magnification is always going to come with that specific, the things you're going to be looking for are equal increase in a OID. That just means elevation away from the image receptor, and you've got magnification. So unequal is always going to be shape distortion, foreshortening, and elongation. So also we have some complicating factors as well. If we have thick anatomy, then we're going to have more distortion. We're always going to have shape, size distortion present, but if we have an angulation on central ray, then we're going to have an increase in distortion, shape or size, either one. Object position will also affect it. So you've got a hypercenic patient, you're looking for kidney stones, then naturally the kidney stone is going to be further away from the image receptor in a hypercenic patient than what it's going to be in an asthenic patient. Your kidneys are about a third of the way through your body. Okay, so if you have somebody, pediatric patient, and see a whole lot of kidney stones in a pediatric patient, but if you had a pediatric patient and you were looking at their kidneys naturally are going to be closer to the image receptor. You know, you have a 400-pound man, and they're going to naturally be at a greater distance. So what that's going to affect is OID, but also if you're doing any kind of exam where you have to put a central ray angulation on the anatomy, or angulation on the tube, the anatomy is going to be projected further away because we have a greater distance. So the OID is going to be greater, and therefore the projection is going to be further away. So it depends on object thickness, object position, where it is in relationship to the image receptor, and object shape. Remember, there's a specific shape that you're always going to have distortion on, and that would be spherical, right? So also with object shape, though, we talked a little bit about it last week in the L spine. Always going to have some sort of distortion in L spine because of the curvature of the L spine compared to the divergence of the central ray. But remember, in your wrist bones, you also got that same issue going on. You remember what we talked about first semester and second semester imaging about the wrist bones is that they're conical in shape, right? So with them being conical in shape, they more closely follow the divergence of the central ray if you shoot them AP as opposed to PA. And I've not in my entire career in imaging had anybody answer the question, why don't we shoot our wrist bones AP as opposed to PA? Nobody seems to know. Maybe it's easier for the patient to do this than to do, shoot AP. I don't know. Nobody can answer that question. So shape distortion and quality control, we have a couple of things. One being vertical beam alignment, and what that involves is a cylinder. I should have pulled this out, but a cylinder And what cylinder has is it has a hole on both ends of the cylinder, okay? So if you make an x-ray of this cylinder, then you can see a change in density where that hole is, okay? They should be directly on top of each other, one in the center of the top of the cylinder and one in the center of the bottom of the cylinder. And what you have is you have a template that you put the cylinder on top of, and you make an x-ray of it. You center directly on that top hole. And ideally, the two should be projected directly on top of each other. That template, though, has a couple of little circles on it that are radiopaque. So what you do is you put the cylinder directly on that template, on the crosshairs of this template, and you make an exposure, and if it's outside that second circle, then your x-ray tube is tilted in one direction or the other. Even if the angulation indicator shows 0, it's still tilted a little bit. And it's projecting that top hole out of regulations. Okay, does that kind of make sense without seeing the exact tool? Kind of makes sense of what I'm trying to get at. So that's the test tool, and it's got to be within that second circle. And it seems like it's 2% of SID is what it should be. So focal spot, remember that the entire target is not your focal spot, or the entire disc is not the focal spot. The focal spot is the actual area of bombardment. It's typically 15, 17 degrees, and it's affected by two things. One being the angle on the amount of bevel that the anode has, but also the size of the stream of electrons that come across the tube. So the size of the filament controls it, and the angulation of the anode controls it as well. Silence that. Bring it up. And just kind of show you what I'm talking about. Because the stream of electrons is pretty obvious, right? You're going to get a sharper image out of that than out of that. Okay? Because you're going to have a smaller stream of electrons. But at the same time, you've got your anode, and the angulation on the anode is 15, 17 degrees. So if we use a smaller focal spot, we're going to make it a little bit bigger than what it is there. We use a smaller focal spot, and our electrons are confined to an area. We've got a very good focusing cup, and are confined to that size of an area, then our projected focal spot is going to be this big, right? So we have a word for this focal spot, and that is a what? Actual focal spot. Right, actual focal spot. This is the effective focal spot or projected focal spot, right? So now let's change the angulation and make it more of a 45-degree angle. So if we flatten this out like that, and we continue our stream of electrons to here, okay, so our actual focal spot here was that big, right? What is it now, in a word? Bigger. That's the word. Bigger. It's bigger, right? So now let's look at what happens with our effective focal spot. What is it? And I kind of cheated a little bit there. I drew it at a little bit of an angle. I'll make it more vertical. In a word, what is that? Same word. Bigger. Bigger. Right. So not just the thing that affects your focal spot and your sharpness or recorded detail because of the focal spot is not just the size of the filament. It's not whether or not you're standing on the rotor and creating a ballooning effect, but it's all of that stuff. It's all of that stuff, plus it's the angulation of anode, the bevel. How steep is the bevel? The steeper it is, the smaller the number it is. If we make it steeper, then all of that works in the opposite direction. We get a smaller effective focal spot, smaller actual focal spot, and we get a sharper image. Right? So what is the line focus principle? Well, that's what I just described. It's the difference between an actual focal spot versus a projected focal spot. It's our ability to create a relatively small focal spot, effective focal spot, while maintaining a larger actual focal spot. So how does that benefit us? We can spread out the heat on a larger area on the target and on the anode, and therefore, and spreading out the heat, it extends to the life. Increases load capacity. All right, so with that though, and it's not just because of that, if we have small, tiny pieces of what are effectively matter traveling at really high speeds and they hit something, the chances are some of those are going to bounce, right? So during exposure, you still got a positively charged anode and a negatively charged cathode and electrons, right? So if the anode end is still positively charged and the electrons are negative, where are they going to try to go? Back towards the anode, right? And if they make it to the anode, high enough energy, they're still going to potentially create an X-ray photon. So we have two things that we have a tendency to kind of conflate. One, and they're really, by the strictest definition, they're kind of the same thing, but we're going to call them something different. If you balloon your space charge and then you send those across the X-ray tube so that the area of bombardment that you intended to use is bigger because you've stood on the rotor button too long, you got a balloon space charge, then it's creating X-rays that are not on the focal track that you intended to use. So by the strictest definition, that would be off-focus radiation. But that's not really what we're going to call it. We're just going to call it increase in effective focal spot size, actual focal spot size because of ballooning of the anode. Okay. Off-focus radiation are those bouncing electrons. They hit, they bounce off, they're still attracted to the anode, so they re-accelerate towards the anode, and then they create X-ray photons somewhere aside from the focal track. Okay, so there's a few of those. If you ballooned your space charge, you're going to create a lot of them, but that's ballooning the space charge. We will also create a few off-focus radiation because of those bouncing electrons, essentially. All right, so there a couple of things that are not well defined on this. First off-focus radiation works with small focal spots. Any kind of blooming or any kind of enlargement of the actual focal spot is worse with small filament sizes. If you read into Bushong's where it tells you what the allowances are for focal spot sizes, what you'll find is the smaller the focal spot size, stated focal spot size, the larger it can be measured and still be within regulations. For example, if you're looking at a microfocus tube and the focal spot size is stated to be 0.5 centimeters or 0.5 millimeters rather, it can be as much as 1 millimeter and still be okay. It can't be over that. But if your stated focal spot size is maybe 1.3, it can only be about 30% over that. So the smaller the focal spot size, the harder it is to contain those electrons just down to that focal spot size. Okay, so it's not just a product of blooming or a product of off-focus radiation. It's pretty much all focal spot sizes behave that way. All right, so there is no effect on contrast or density with a focal spot. And where you're going to trip up on this is on density or exposure. Okay, so you got a couple of things to consider here. Mass is mass. That's number one. That's what you need to lock into your head is mass is mass. So if you make an exposure of 100 mass on a small focal spot, you make an exposure of 100 mass on a large focal spot, mass is just a count of electrons, right? So your exposure should be identical regardless of which one of those focal spot sizes you're using. The thing that's going to catch you though is that you're going to equate that with, well, I can't make an exposure of 100 mass on a small focal spot, which some machines, especially if you select a high MA station, will disallow you from making that exposure. That's not the same thing, okay? That's you. If you can't make the exposure, you can't really compare two exposures. Does that make sense? If the machine says, no, you can't have that, you can't really compare that to, a larger focal spot where you can actually make the exposure. So in that way, you're not going to have any difference in exposure between small and large focal spot, right? 100 mass is 100 mass, 50 mass is 50 mass, 20 mass is 20 mass, regardless of what size focal spot you're going to use. So the heel effect, I'm going to bring this back up and we're going to take a look at the heel effect. And where it's worse. We've got two different things in the heel effect. You've got what we recognize as a heel effect, and that is that radiation intensity is going to be worse, or not worse. You're going to have more intensity on which end of the X-ray tube? Cathode end of the X-ray tube, right? That's because of the likelihood of absorbing some X-rays that you create in the anode itself. So you create X-rays here, they can't get through the anode. You're going to have less intensity on the anode end of the X-ray tube. But at the same time, you're going to have a difference in sharpness or recorded detail between cathode and anode end of the X-ray tube. So since we're coming off at an angle, right? We're coming off our anode at a bit of an angle. What I'm going to do is I'm going to create X-rays here. They're going to go off with equal intensity in all directions. We have a word for that. That is isotropic emissions, right? So we're going to have X-rays that are created here, and they're going to exit the window. We're going to put the window right there. They're going to come through the window right there. Okay? Divergence of the central ray. Some of them are going to come out there. Some of them, though, are also going to come out over here. Right? Because it's isotropic emission. And the same is going to, I can draw a line for each one of those, but you get the point. We're going to have X-rays that come off of this portion of the anode that are going to exit this end of the window. They're going to exit that end of the window, and then all the way across as well. Right? Then we're going to have also, let's say our focal tract ends right there. We're going to have X-rays that are created here, and those are also going to exit this end of the window. Right? We're going to have some that are created here, and they're going to exit that end of the window. True? And then all the way across. So let's say we put a patient's anatomy, patient's too small, so we put patient's anatomy right here. So what that means is that we're going to create X-rays that come off of this portion of the anode, this portion, this portion, this portion, this portion, all the way down, so that it's going to catch the edge of the anatomy and give us a density on our image receptor right there. You with me so far? We're also going to create some, they're going to hit it, and they're going to give us a density right here. Okay? So what do we call that? Double shadow, loss of sharpness at the edge of an anatomy. What do we got a word for it? It's focal spot blur. We got another word for it. It sounds like what you would need today because it's a rainy day. Penumbra. It's penumbra. Umbra is sharpness. Penumbra is unsharpness. So that is your penumbra on the anode end of the X-ray tube, right? But over here, we're going to follow it down. We're going to create a density there. This one's going to completely miss it. This one here is going to hit it, and we're going to have greater separation. It didn't really bear that out in the drawing. Thank you. Maybe here. And what do we have there? Is that bigger than this? The answer is yeah. So where is the penumbra greatest? The cathode end of the X-ray tube or the anode end of the X-ray tube? Cathode end of the X-ray tube. We have less sharpness on the cathode end of the X-ray tube. Sharper on the anode end, less intensity. Unsharpness on the cathode end of the X-ray tube, more intensity. So the anode Hill effect has two different things. One is not just the difference in density or difference in exposure, but also we have a greater amount of blur on the cathode end as well. We tend to talk about the difference in intensity much more than what we do the difference in unsharpness. So anode Hill effect, we just kind of ran through that. Subject factors, we kind of ran through this somewhat. With patient thickness, we have more attenuation. We're going to lose some. We're going to lose a greater amount of our X-ray beam. We're going to have less intensity at the image receptor. We're going to create proportionally more scatter radiation. We're going to see some differences in mass and tissue mass on the image, and it can potentially affect subject contrast. So it used to be pretty obvious the difference in contrast between, let's say, sthenic and hyposthenic patients, right? But the adjacent body habiti, you just don't see that much of a difference anymore until you get into some really large hypersthenic patients. And you're going to lose a lot of contrast. And I don't know that it's so much about the scatter radiation as much as it is just the energy of the photons that eventually make it to the image receptor, and an inherent subject contrast, loss of subject contrast throughout the patient. So your subject contrast is provided by your Z effective. You'll see it referred to as Z number, Z effective, or even ZEF number, ZEFF. ZEF number just means your effective atomic number. And that's average atomic number of the tissue type, and what's the atomic number of bone? Well, what's bone made out of? It's made out of a lot of different things. You got magnesium, you got calcium. So you can't really say it's got its own atomic number. It has an effective atomic number based on what it's composed of, right? So with patient thicknesses, you have differences in OID. That's going to give you distortion. We're going to have, especially if we introduce angulation on a central ray, we're going to potentially project our anatomy much further away than what we will with a patient who's asthenic. You see that if you remember back to when we were talking about lordotic chest x-rays, right? And clavicles. If you had a patient who was really thick, barrel-chested, you needed less of an angulation because those clavicles are going to move a whole lot more on a patient who's, really thick. Just a little bit of difference, but if you have a patient who's really thin, you got to move quite a bit, a lot of angulation, right? So you're going to have natural distortion with patients who are thicker. You're also going to have a loss of sharpness reported detail and increase in penumbra as well. And then we've kind of done object shape to death, so we're not going to talk about that. We're not really going to have a change in distortion with the change in KBP. You might have a difference in absorption blur and the appearance of loss of sharpness recorded detail because of the increased penetration in the periphery of something. But that's really a visibility of reported detail rather than an actual sharpness thing. So motion. Remember, we have the two different types of motion. We have voluntary and involuntary motion. So how do you control both of those? Involuntary motion you control with time, right? And how you get to the reduction in time is you got a lot of different ways. What if you photo time? How could you reduce time? I think it's a test question. I think it might be a test question in context of how you might introduce quantum model.
The density.
Okay, density controls, you can increase or decrease your exposure time, but what if you increase KVP? What's going to naturally happen if you increase KVP in your photo time?
Decrease mass.
You're going to decrease mass, overall mass. And typically that's going to reduce time, exposure time specifically. Your MA is generally fixed on your, during your exposure. There's specific types of generators that falling load generators where your MA can change, but for most of your machines, the MA station is going to be fixed. So if you increase your KVP, time just decreases. So motion is the most detrimental thing that would affect your spatial resolution. It's the one thing that you can't control completely. You can control the length of your exposure and reduce the likelihood of seeing a motion artifact, but the patient is 100% in control of whether or not they move, right? So you can't really completely overcome it. Your tools are reduction of time, and how you reduce time would be fast image receptor speeds. You can't really control that anymore. It's set into the system, but if you can change your MA station to high MA station, great. If not, then you could use a higher KVP, but you might introduce a quantum model. Unlikely, but it could happen. So motion looks like that. Sometimes we'll want to use motion though, right? So yesterday we were going through C-spines. What if you have a patient who's in a collar and you need to get an AP C-spine? Patient can't open their mouth. What can you do? If you say fuchs, I'm going to throw something at you. You know how I feel about fuchs. Right? What's that?
Is it the wagon?
Wagon jaw. Exactly. Dot and method. Right? So as autotomo, and this is a lateral chest x-ray is hideous. For a lot of reasons, the guy's sick. Looks like he's got an elevated diaphragm for whatever reason, but he's probably breathing throughout the exposure and introduced motion artifact. Okay, so contrast resolution. Contrast resolution, remember, whenever we're talking about resolution types, if your question just says resolution, then what are we talking about? Contrast resolution or spatial resolution? Spatial resolution. Spatial resolution, right? So contrast resolution is always going to come with that quantifier as contrast resolution. And it just means contrast, right? It just means difference. So it's the ability to see those similar shapes, small objects as separate entities. So it's contrast resolution. So it's your ability to visualize things like the kidneys on KUV. You know, you should be able to pick those out now. First semester, we're just glad that you could pick out the spine on KUV. You know, but you should be able to see the kidneys now, psoas muscles. In certain patients, you might actually be able to see the inferior quarter of the liver. That's more rare than the other things. But those are similar shaped, or not similar shape, but similar density, patient density, similar atomic number structures, right? So your contrast is what enables you to visualize those things. So it makes the diagnosis of pathology possible. Patient has a kidney stone, especially if it's a calcium-based kidney stone. That's abnormal inside the kidney. Kidney doesn't have any bones in it. So you see calcium inside the kidney, and you understand that you've got a disease process going. So it's affected by tissue type, tissue thickness, and to a much lesser degree, KVP. So this patient is obviously quite large. You see multiple rolls here. So this patient, even on a digital image, is going to demonstrate low contrast. So I think this is actually a screen film image, but I mean, I can't make any kidneys out on this, but that might be one right there. Can't make this one out. We've got fecal matter as well. So it's still applicable, and it's still, in hyperstenic patients, you're still going to see a loss of contrast. This is a higher contrast one. Now we can see that kidney, we can see a portion of this kidney, psoas muscles, very, very much a higher contrast image. Low contrast, looks milky. High contrast, higher contrast, much more black and white. We have a tendency to focus on chest x-ray and say, we want to see a chest x-ray with low contrast. We don't want to see it like this, right? That's got some sort of problem. Even if this says it's a film image, and I don't doubt that, but even in screen film radiography, that's an ugly gray image. So Babe Ruth, if you don't know who that is, he was a baseball player a long time ago. So what you've got then is high contrast, low contrast. Okay. So what causes poor contrast resolution? A lot of things, as mainly the patient, patient factors, or potentially selecting the wrong algorithm. We saw that today that might not affect much at all. But in KVP, previously, KVP was our primary control of contrast when everything else was right. But anytime we lose photoelectric interactions, we're going to have a loss of contrast. So increasing KVP increases scatter the most. Anytime you introduce scatter, you have a possibility of losing some contrast. The things that affect your average energy, remembering back to your brim spectrum, if we increase our filtration or our tube ages, when we get an increase in inherent filtration because of tube tanning, we might lose some contrast. From single phase to three phase, if you remember in the brim spectrum, it pushes everything to the high energy side, increases our numbers, but pushes towards the high energy side, potentially could lose some contrast there as well. Same thing from three phase to high frequency, only it's less dramatic. But really where we get it is increased thickness of the tissue type, or if we have water type structures, if the patient becomes edematous. You go shoot a KUB on a patient one day. It's the day they checked into the hospital, and they're relatively healthy for somebody who just checked into the hospital. You go back 3 days later and they look like just a water bag. They're full of water, right? They've been pushing fluids into this patient and they're full of edema. You're going to see a difference in the contrast on their image. You've just got more water to penetrate. Okay. So anything that adds too much density, in this case it will be way overexposure of patient, or anything that adds noise, which would be, again, scatter or quantum model. So in that, what we're talking about are visibility functions, visibility recorded detail. So fog, scatter, double exposure, incomplete erasure. Again, usually that's going to be a CR issue. Reader errors, CR issues, improper collimation could cause that. Selection of incorrect algorithm. Fluorescent lights actually add fog to your CR sets. So I think I mentioned that last week or week before. If a CR set is left unused for as much as 8 hours, it needs to go through the eraser bank. Otherwise, it's going to have so much fluorescent light fog and background fog on it that it's going to affect the image. So excessive exposure, improper KVP selection is probably not going to do a whole lot to it. But so sharpness of recorded detail versus visibility. Again, when your questions are asking you about sharpness of recorded detail, it's going to be sharpness or recorded detail sharpness or resolution, as opposed to visibility functions are typically scatter radiation, fog issues, contrast resolution. So it's just a foggy image, right? This is not an X-ray, but a foggy image of trees on a hillside. Either that or somebody turned the camera, one of the two. But you see the trees. The trees look like they're grown at an angle, so somebody was probably had a tilted image. So you can't see them very well, right? Right? Are they there? Yeah, they're there. So sharpness to recorded detail, they're there. Visibility is can you see, right? You got to have them both. So the dynamic range, the contrast resolution is what we're looking at for CR and DR over film. The image was always there. It's just that we couldn't pick it out all that well. So that's how it is that CR and DR has improved our image. So things that control it, beam limitation, KVP, accurate KVP, beam limitation, we got PBLs, positive beam limitation, don't really apply as much as what they used to. You know, if you select an exam, it might control your collimation. That's a kind of an extension of positive beam limitation. Cones and diaphragms, you don't see all that much anymore. So, but what we do also have are three different things that we can use to clean up scatter radiation after it's created. So this is pre-creation. You could also add into pre-creation compression of the tissue. Just don't see that a whole lot anymore, but it is a testable question, so you might add that in there. But removal of scatter after it's produced, typically grids. You might have such things as post-patient collimators, and we see that more in CT than anywhere else. But there are some dedicated chest X-ray rooms that use, rather than an area beam, and that's what we use as an area beam in diagnostic, but in these dedicated chest rooms, they'll use a fan beam. So it's collimated real tightly so that the beam, you know, looks like something off a sci-fi movie. It just goes up and down the patient and, you know, lengthwise. And when you make your exposure, that beam scans across the patient. And at the same time, you've got some post-patient collimators that go with it. All right. So what the post-patient collimators are is kind of like a single shot grid. Okay. So the purpose for them is to eliminate anything that's wide angle scatter radiation. So it's kind of like a grid, post-patient collimators, and then air gap. You know, they say we don't need a grid on chest X-ray because of natural air gap, right? Also say we don't need a grid on the lateral C-spine because of the air gap. Works like a little ratio grid. I would also add into this digital grids. All right. So my understanding of how digital grids work is that you make an exposure and your machine being calibrated, it knows what KVP that your X-ray tube should be putting out, right? And because of the filtration, 2.5 millimeters of filtration minimum, it knows what KVP, minimum KVP it should be receiving, the image receptors, okay? So if it receives X-ray photons below that level, then it knows that that's scatter radiation. It just disregards it. It just picks that one out and throws it away, and it says, you know, we're not going to use that in the analysis and creation of this image. So it works like a grid, but it only selects those very low voltage, kilovoltage X-ray photons. Does that kind of make sense? A little bit? Mm-hmm. Yeah. Okay. So they're effective, and they're probably more effective than the air gap, probably not as effective as physical grids. I think they'll probably dial that in a little bit better over time, and they'll become more effective. Where they are, the benefit of a digital grid versus a regular grid is in patient exposure. So If you're taking an X-ray on a thin patient's abdomen, let's say a pediatric abdomen, probably better to go with a virtual grid than a traditional grid. So what's your grid conversion for a 10-to-1 grid? You got to increase by a factor of, remember? It's about 4. It's about 4 times the mass. Virtual grid's about 2. So you got a pediatric patient developing sex organs. You're taking a KV on a patient. Which one is better to use? Even if you lose a little bit of contrast, just a little bit of contrast, which one would be better to use? Virtual grid, right? Instead of exposing the patient to 4 times radiation exposure, virtual grid, much better. So I think they'll dial those in. Do I think the grids will eventually completely go away? Maybe. I don't think anytime soon, but maybe. If they can make the virtual grids that much better. So overall image quality, good positioning, low OID, good SID. Make sure that the alignment to between your central ray, your image receptor, and your point of interest is as it should be. And sometimes we have to use a central ray angulation. Just make sure your central ray angulation is right and in the proper orientation to your image receptor and your anatomy. Good patient instruction, good resolution image receptors, good technique, adequate KVP, adequate MA, shortest time possible, and use grids of collimation where appropriate. Okay. So we just talked a lot about a lot that was in chapter 22, so we're not going to begrudge these things. Factors of control, creation, scatter, KVP, field size, patient thickness, KVP. Of those 3 are the least significant in image creation now. 4 paths of X-ray interaction. You got scatter away from the image receptor. Oops. You got total absorption, transmission without any kind of interaction in the patient, and then you've got your Compton scatter. That's where your dose comes from, is Compton scatter radiation. KVP, as KVP is increased with no other changes, then what we get is an increase in tube output. Penetration of the photons is increased, but all interactions increase. So if the only thing that would change is KVP, then what we get is a greater output from the X-ray tube. Okay, I conflated 2 things there. If we just increase KVP, we get a greater output from the X-ray tube. Remembering your brim spectrum. Okay, what happens when we increase KVP? What happens to the brim spectrum? Pushes to the higher energy side. So those higher energy photons, we get a lot more of those, but what else do we get? The height goes up as well. So we get a greater greater number of X-ray photons that we create, right? So most of those are going to be higher or lower energy. Higher. Okay. So what is the average energy of the X-ray? Any X-ray beam? About 1/3, right? So we get a tremendous number of low energy X-ray photons still created, right? So if we increase KVP, and that's the only thing that we do, then we're going to get more interactions inside of the patient. Those high energy X-ray photons, they're going to be a lower incident of those interacting inside of the patient. But the beam itself, we're going to get more interactions inside of the patient. Does that kind of make sense? You with me so far? Those high energy photons are going to go through the patient, but the highest number of photons that we're going to create are going to be low energy photons, right? Because it's still 1/3 of the overall energy of the X-ray beam. So we create a 120 kVp X-ray beam. What's a third of the energy? 40, right? So what do you use 40 kVp for? When's the last time you set 40 kVp for exposure on patient? You never have, right? So those 40 kVp X-ray photons are going to, they're going to create a lot of interaction inside of the patient. So tube output increases, penetration increases, all interactions increase, but scatter increases more than what PEs do. All right, so that creates more fog. Field size, as you increase your field size, you expose more tissue, you expose more tissue, you create more scatter radiation, right? So beam restriction limits that scatter radiation. Lower scatter production equals lower exposure to the image receptor. So anytime that we introduce collimation or field size adjustment, then it needs to come with a technique adjustment as well. You kind of play around with this too. Take you a basin of water or something to make an exposure on in clinicals, right? So expose the entire thing, make your exposure, and then collimate down and make a second exposure. And you should see a difference in how much mass you use, providing you're using automatic exposure control. So if you collimate down, what you should see is an increase in mass. You're not creating that scatter radiation. Some of that scatter is going to hit your automatic exposure and terminate the exposure. So if you limit the amount of scatter that you create, likewise, it's going to limit the amount of scatter that hits your automatic exposure control. So your technique is going to be a little bit different. So beam restriction, originally for radiation protection, now it improves visibility, reported detail, reduces scatter radiation. All the different types, talk about that. Just don't see those anymore. Again, if you don't make an adjustment to your technique's going to come out underexposed. S number should demonstrate that. Remember, you have two different sets of collimators. You got the first set being a multi-leaf that you don't see. The collimators that you do see are those shutters, right? The purpose for the multi-leaf collimators is to limit the amount of off-focus radiation that's going to be emitted from your X-ray tube. So it limits off-focus radiation. It's still primary radiation. You're going to have questions that you're going to trip up on this one as well. Off-focus radiation, remember you've got primary and you have secondary radiation. Primary radiation is what comes out of the X-ray tube before it interacts with the patient. It's primary beam. Secondary is what comes through the patient, right? So your off-focus radiation is primary beam. It's just primary beam that you don't want. Okay, so it's kind of like, you're going to have a tendency to think of it kind of like scatter. Yeah, but it's scatter coming from the X-ray tube, right? So it's from the X-ray tube and not from the patient. Therefore, it's primary beam. You're going to have a tendency to say it's secondary radiation. It's not. It is primary radiation. Light localization, the purpose for the mirror, remember, is to reflect the X-ray beam. Remember also that the mirror is at a perfect 45-degree angle, right? So we're going to talk a little bit about QA on this. It's at a perfect 45-degree angle so that the light off to the side is reflective of the beam that's coming through the mirror, right? So your collimators can be off by like 0.8 inches if you're shooting at 40 inches, okay? That's about the size of a penny. So when you go into clinicals, if you have some pennies on you, you can measure the accuracy of your collimators. I think a penny is actually 3/4 of an inch. So, 3/4 of an inch is 0.75. So 40 inches, if you're shooting 40 inches, 0.8 inches. That's the same. At any rate, a lot of things can cause a dissimilarity between your X-ray beam and your projected light field. One of which is your mirror, because of rough handling, being banged around a lot, can drop a little bit. So what that's going to cause is instead of that 90-degree projection of your light field, what it's going to do is it's going to take your light field and it's going to project the entire light field in a different direction. So if you use the pennies or you use paper clips or whatever to put at the edge of your collimated field, if your entire collimated field is shifted in one direction, that's an indication that your mirror is at an angle. Okay. Sometimes your shutters, they're motor driven and they've got little gears in there. Sometimes your gears slip. And what happens then is one shutter is open wider than the other. Those are the two most common collimator issues that you're going to see. So collimators should be within plus or minus 2 inches or 2% of SID, form the same time as your beam perpendicularity, the cylinder type thing I was describing before. Okay. So that's your setup. These are the shutters you're familiar with. The multi-leaf is up here. Off-focus radiation is reflected by this little ding right there on the nut that's holding the anode onto the anode stem. And that is not to scale. So we've kind of done this to death. Some pathological conditions that might add or increase your ZEP number would be things like acromegaly. You get an increase in bony tissue. That could be caused by pituitary tumor, right? Something that might decrease will be a bowel obstruction. So some things that you might want to pay attention to in clinicals, you walk into the patient's room and the patient looks puffy. Well, you haven't seen the patient before. What's causing the patient puffiness? You know, they got a big distended abdomen. Cause of that? You know, is it the patient's normal anatomy? Do they have a great big beer belly? Do they have some other complicating issues like sickle cell? You know, some of your sickle cell patients will have a big abdomen. Or are they full of fluid? What are your telltale indicators the patient's full of air? Bowel obstruction. NG tube. Yeah. If they have NG tube in, and that NG tube is hooked up to suction, and there's bile in the canister, 9 times out of 10 that patient has a bowel obstruction. Well, okay, you think of bowel obstruction, well, you know, you keep putting stuff in, and it's not coming out, then it's all solid matter inside of the patient, right? So you need to increase your technique. Bowel obstruction, they're full of air, right? So if they're full of air, you definitely don't need to increase your technique. You may need to decrease your technique. As opposed to you walk into the patient's room and they look puffy all over. They got a mask on and the elastic in the mask is kind of pushing into their skin, right? And it looks like, you know, you laid something on a memory foam mattress. They're probably full of fluid. So if they're full of fluid, you're going to have to adjust your technique too. And in this case, you're going to have to increase your technique. What you can do, you know, just to verify, is that, you know, find someplace on the patient's skin, you know, wrist or ankle, somewhere where bones are usually not too far under the skin, right? And if they're full of fluid, they're going to be further under the skin. You mash on that and you just look for the rebound. If it comes back pretty quick, that's not edema. That's just their anatomy, right? But if it comes back real slow, again, like kind of like a memory foam. You ever mashed on memory foam? It doesn't just bounce right back up, kind of reinflates. So if it comes back like a memory foam, that's indication the patient's full of fluid, and you would need to increase your mass in that case. So technique adjustment still is typically mass. If you increase your KVP, again, you change your, you know, the Compton P ratio, you change your scatter, you change everything, really. I think though, and I'm gonna beat this to death, I think though that at some point in your career, that's gonna be the technical factor of choice for changes in size and composition, KVP, because it really doesn't affect contrast all that much, even though it does still affect scatter creation, just doesn't affect contrast all that much because of computer algorithm. So, for now, though, that's my opinion. For now, though, the accepted adjustment for size, tissue composition, unless it's something that we need to increase the penetration of, like acromegaly, your technical factor of choice is going to be mass. Right. Okay. So, whenever you're phototiming, though, and since you need to increase the density or the exposure to the image receptor, you're not going to select patient size differences or plus or minus one densities on your control panel. Right? You use those for sometimes for positioning when you know the positioning is going to be difficult to put the anatomy of interest directly over the photocell. You use those. Or if you intentionally need to increase the exposure to the image receptor, you use those. But if, barring those situations, whenever you're phototiming, you should not have to change your technique at all, right? I know some of your pre-programmed things, you push asthenic patient, and it might give you, say, 100 kVp for a chest x-ray as opposed to hypersthenic may give you 120 kVp. And that's fine. That's how the manufacturer set up the machine. That's fine. But if you were to shoot a hypersthenic patient with 100 kVp, you're not going to see it that much of a difference on your image than if you shot it at 120 kVp. Because what's controlling your exposure to the image receptor? Your ACs, right? What's controlling the contrast and density on your image? The algorithm, right? You look up the, so theoretically, you shouldn't have to adjust anything whenever you're using AECs. Compression, I mentioned that before, might decrease scatter radiation. You just don't see it used a whole lot. Grids. Why don't we pull up there? We'll pick up with grids next week. We talked about grids earlier too. But we'll pick up with that next week.